We are starting with a new chapter, that is elements of group 16, 17 and 18. Group 16, 17 and 18 are collectively called as p block elements. We have already studied group 13, 14, 15 in 11th standard. So from group 13 to group 18 constitute the p block elements. How would you define the p block elements? So when the differentiating electron or the last electrons enter into the p subshell, then it is called as the p block elements. P subshell has a capacity to occupy about 6 electrons. A maximum of 6 electrons can be filled in the p subshell. In this chapter, we are going to study group 16, 17 and 18 elements in detail. Now we shall study the occurrence of each element. The elements like oxygen, sulfur, selenium, tellurium and polonium belongs to the group 16 elements and it is called as oxygen family. And the metal ores belonging to this family are in the forms of either oxides or sulfides. Oxides are those which contain oxygen atom and sulfides are those which has a sulfur atom present in it. Group 16 elements are also called as chalcogens or ore forming elements. Oxygen is the most abundantly found element on the earth. About 20.95% of oxygen is present by volume of air and 46.6% of oxygen by mass in Earth's crust, whereas 0.034% of sulfur by mass is present in the Earth's crust. Sulfur occurs mainly in combined form like gypsum, which has the formula CaSO4 twice H2O, Epsom salt, which has the formula MgSO4 7 times water, barite, that is BaSO4, and sulfides like galena, that is PbS, zinc blende ZnS, and copper pyrites with the formula CuFeS2. Selenium and tellurium are also found as metal selenides and tellurides in sulfide ores. Polonium is radioactive in nature and it is the product of uranium and thorium. Now we move on to the occurrence of group 17 elements. Fluorine, chlorine, bromine, iodine and astatine form the group 17 elements. Group 17 elements are called as halogens. The Greek word halo means salt and gene means form. So halogens are salt producing elements. Halogens are said to be very reactive in nature because they have high electronegativities. Now how do they get this electronegativity character? Because they take electron and they get that minus sign which makes them electronegative. They can accept electrons from other elements. Halogens never occur in free state. They are always in the form of compound, which means they are not freely available and they will be present only in combination with some other element. Fluorine occurs in the form of insoluble fluorides like fluorspar, cryolite and fluoropatite. Fluorine is also present in small quantities in soil, fresh water plants and in bones and teeth of animals. Seawater contains chlorides, bromides, iodides of elements like sodium, potassium, magnesium and calcium. Marine life also contain iodine in their system. For example, seaweed contains about 0.5% iodine and chili saltpeter contains about 0.2% of sodium iodate. Astatine is the last member of the halogen family. It is radioactive in nature. Its half-life is 8.1 hours. Half-life is the time it takes for the concentration of that substance to fall to half of its initial value. The elements helium, neon, argon, krypton, xenon and radon form the group 18 elements. All the noble gases are present in the atmosphere except for radon. About 1% of these noble gases are present in the dry air. Argon is the main constituent of dry air. The main commercial source of helium is natural gas. Xenon and radon are the rarest elements belonging to this group. So this was the occurrence of elements of group 16, 17 and 18 respectively. Now we move on to study the electronic configuration of group 16, 17 and 18 elements. The general electronic configuration of group 16 element is Ns2Np4. Let us take the first example of oxygen, which is having atomic number 8. Let us write the electronic configuration for oxygen. So it is 1s2, 2s2 and 2p4. So 4 plus 2 plus 2 is going to give me 8. So the last two shells, that is S and P, S is completely filled with 2 electrons and P is filled with 4 electrons. So in place of 2s2, 2p4, we can write it as ns2 and np4. Let's take the second example of sulfur, which is having the atomic number 16. Hence the electronic configuration of sulfur is written as 1s2, 2s2, 2p6, 3s2, 3p4. So again, if you observe the last two shells, that is 3s2 and 3p4, again the S has 2 electrons and P has 4 electrons. Hence it proves the electronic configuration of group 16 elements is Ns2Np4. Now we move on to group 17 elements. The general electronic configuration of group 17 elements is Ns2Np5. Let us take the first example of fluorine, which is having the atomic number 9. So the electronic configuration is written as 1s2, 2s2 and 2p5. So if you check the last two shells, that is S and P, S has 2 electrons and P has 5 electrons. Hence the general configuration of Ns2Np5. Next example is of chlorine, which has the atomic number 17. Electronic configuration will be written as 1s2, 2s2, 2p6, 3s2, 3p5. So here again the last two shells, that is S and P, S has 2 electrons and P has 5 electrons, and hence it is proving that the general electronic configuration of group 17 elements is Ns2Np5. The general electronic configuration of group 18 elements is Ns2Np6. The first example is helium, which has the atomic number 2 and the electronic configuration is written as 1s2. Next example is of neon, which is 10. The electronic configuration is written as 1s2, 2s2 and 2p6. So if you check the last two shells, that is S and P, they are completely filled with 2 and 6 electrons each. Next example is of argon, which is having 18 electrons and the electronic configuration is written as 1s2, 2s2, 2p6, 3s2, 3p6. Again, if you check the last two shells, that is 3s2 and 3p6, it has 2 and 6 electrons, which means the shells are completely filled with the maximum capacity of electrons. Hence the general electronic configuration Ns2Np6. The electronic configuration given in the chart is in the form of condensed form, which means noble gas is used to write the condensed form electronic configuration. The reason behind that is noble gas has the stable electronic configuration because the shells are completely filled with the number of electrons which they can occupy. We know that S can occupy 2 electrons and P has the capacity of occupying 6 electrons. You can say that the electronic configuration is stable when the shells have half filled electrons or completely filled electrons. For example, we know that S has the capacity of filling up 2 electrons. So even if it has 1 electron, then it is going to be stable. Next is P. Completely filled is 6 electrons and half filled is 3 electrons. In both the cases, it is going to be stable. For D, capacity is 10 electrons. So completely filled is going to be 10 electrons and half filled is going to be 5 electrons, and in both the cases it is going to be stable. For F, completely filled is 14 electrons and half filled is going to be 7 electrons, and in both the cases it is going to be stable. Now we move on to study The atomic and physical properties of group 16, 17 and 18 elements. First is atomic and ionic radii. In group 16, 17 and 18, the atomic and ionic radii increases as we move down the group because there is increase in the number of quantum shells because of increasing atomic number. When you move across a period, that is from left to right, the atomic and ionic radii decreases with increase in atomic number, consequent to increase in ZF, which is the effective nuclear charge. What does this mean? Now we know nucleus is in the center, then you have the quantum shells. Now each quantum shell is going to have its respective electrons present in it. More the quantum shells, less will be the nuclear charge trying to attract the electrons which are present in the last valence shell. Because since we know that electrons are negative in nature, so they are going to repel each other, and also these electrons which are present here are not going to allow the force of attraction of nucleus to reach to the electrons which are in the last valence shell. Z effective is the nuclear charge. Group 17 elements, which are the halogens, have the smallest atomic radii in their respective periods. Next is the ionization enthalpy. Now what is this ionization enthalpy? This is the nucleus, then we have the first shell, second shell, third shell, fourth shell. In each shell there are electrons present, right? And these electrons are going to repel each other since they have the same sign. Now the nucleus tries to attract these electrons towards itself, but I told you the electron which is present in the valence shell is not able to get that force of attraction of nucleus because these electrons present here try to shield it. Okay, so now though these electrons present here are trying to shield the force of attraction of nucleus, there is some amount of force which is reaching this particular shell here. Now if I want to remove this electron from here, I need to apply energy which has to overcome the force of attraction of nucleus. Okay, and this energy which I am applying is in the form of heat, and we know heat is also called as enthalpy. Now the example that I gave you here was an example of atom. If I am removing this particular electron from here, then it is going to get a positive charge and it is going to get converted into an ionic form, right? Hence it is called as ionization enthalpy. So it is the amount of energy that is required to remove the electron from the valence shell. The group 16, 17 and 18 elements have high ionization enthalpy. The ionization enthalpy decreases down the group due to increase in the atomic size. Here are two atoms, one which is having only two shells and the other atom which is having say 5 shells. Okay, and the electrons are present in all these shells here. Now we know that the nucleus has force of attraction, or it attracts this electrons towards itself. Okay, I told you as the number of shells increases, the nucleus won't be able to reach out to these electrons, right? Now if in case I want to remove this electron here, of course I have to apply more energy because it is more strongly attracted to the nucleus. But if I look here in the second case, if I want to remove this electron here, of course the energy that I am going to put is going to be less, because this nuclear force of attraction won't be reaching to this particular valence electron here as it was reaching in the first case. Here the nuclear force of attraction was very strong, whereas here this electrons present here are going to shield it. Okay, so here I have to apply less energy to remove this electron. So that is what they are saying. As you move down, as the atomic number is increasing, the shells are also increasing. The nucleus is not able to reach out its force of attraction to the electron which is present in the valence shell, and hence if this force is not reaching this particular electron, then I can easily remove this electron by applying less amount of energy. Across a period, ionization enthalpy increases with increase of atomic number. This is due to addition of electrons in the same shell. However, the elements of group 16 have lower ionization enthalpy values compared to those of group 15 in the corresponding periods, owing to extra stable half-filled electronic configuration of p orbitals in elements of group 15. As we move down the group, the size of the atom increases in this manner. When we move across the period, it is going to decrease. So of course here, where the size of the atom is less, you will require more energy to remove the electron because it is strongly attracted to the nucleus. But where you have atom of a bigger size, the last electron in the valence shell is loosely bound. It is not that much attracted to the nucleus and you will require less amount to remove that electron. The general electronic configuration of group 15 element is ns2np3. Now, we know that when the orbitals are vacant or if they are half filled or completely filled, we say that they are highly stable. So here in case of group 15 element, P has 3 electrons, which means it is half filled and it is highly stable. Whereas group 16 elements have the general electronic configuration of ns2np4. So if we take the P shell, there are 4 electrons. So it is not half filled and hence it is not stable. We know that the elements of group 16 are bigger in size as compared to group 15 elements. According to the theory, more ionization enthalpy is required to remove an electron from smaller atoms. But however, in group 16 elements, more energy is required to remove an electron from the valence shell because group 15 elements have highly stable electronic configuration. Next, we move on to electronegativity. What is electronegativity? Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. In group 16, 17 and 18 elements, the electronegativity is going to decrease down the group. Oxygen has the highest electronegativity, which is next to fluorine amongst all the elements. Halogens also have very high electronegativity. Fluorine is the most electronegative element in the periodic table. It is because it contains 5 electrons in the p shell, whereas we know the highly stable form would be having 6 electrons in the p shell. Since it is very much close to the optimal configuration which is actually required, it is electronegative in nature, which means it has 5 electrons, which is very much close to 6 electrons, and hence it is more electronegative in nature. Next is electron gain enthalpy. Electron gain enthalpy is the amount of energy released when an electron is added to the gaseous atom. In the group 16 and 17, electron gain enthalpy becomes less, negative down the group. But in group 16, oxygen has less negative electron gain enthalpy than sulfur due to its small atomic size. In group 17, fluorine has less negative electron gain enthalpy than that of chlorine because fluorine atom is smaller in size as compared to that of chlorine. Now when we move on to group 18 elements, which are also called as the noble gas, they have no tendency to accept electrons because they have a stable electronic configuration. The general electronic configuration of groups 18 element is ns2np6. So you can see S, which has a capacity of filling up 2 electrons, is completely filled, and P having the capacity to fill up 6 electrons is completely filled, and that is why they have a larger positive electron gain enthalpy. Next, we move on to study the physical properties of group 16, 17 and 18 elements. First, we shall study about group 16 elements, which is also called as the oxygen family or chalcogens. First is oxygen. So we know that oxygen is a gas while other elements are solid at room temperature. Now, oxygen and sulfur are non-metals. Selenium and tellurium are metalloids, which means it is going to have properties which are intermediate between those of metals and non-metals. While polonium is a metal. We know that polonium is radioactive in nature and it has half-life of 13.8 days. The melting and boiling point increases with increasing atomic number, and all the elements of group 16 exhibit allotropy, which means they exist in different physical form. Now we move on to group 17 elements, which is also called as halogen family. Now fluorine, chlorine are gases, while bromine is a liquid and iodine is a solid at room temperature. Fluorine is yellow in color, chlorine is greenish yellow, bromine is red and iodine is violet in color. Fluorine and chlorine react with water. Bromine and iodine are only sparingly soluble in water, which means that they do not completely dissolve in water, but they are completely soluble in various organic solvents like chloroform, carbon disulfide, carbon tetrachloride, hydrocarbons, which give colored solutions. Bond dissociation enthalpies of halogen molecules follow the following order. Bond dissociation enthalpy is the amount of energy required to break the bond in order to separate the two atoms. So the order of bond dissociation enthalpies is chlorine is greater than bromine, which is further greater than fluorine and iodine. So the bond dissociation enthalpy of iodine is very less as compared to that of chlorine. Chlorine requires highest bond breaking energy. Next are the physical properties of group 18 elements, which are also called as noble gases. So noble gases are monoatomic, which means they are made up of only one atom. They are sparingly soluble in water, which means they are not completely soluble in water. Noble gases have very low melting and boiling point. Helium has the lowest boiling point, which is 4.2 Kelvin of any known substances. Now we shall study the anomalous behavior of oxygen and fluorine. Anomalous behavior is the unique behavior which is shown by an element when compared with other elements belonging to the same group. First, we are going to study the anomalous behavior of oxygen. So first point is atomicity. So oxygen is a diatomic molecule, which is O2, while other are polyatomic molecules. Polyatomic molecules means combination of more than two atoms together. So if you look at phosphorus, it is P4 and sulfur is S8, whereas oxygen is diatomic. Di stands for 2. So oxygen molecule is a combination of two atoms of oxygen. Next point is magnetic property. Oxygen is paramagnetic while all the other elements belonging to this group are diamagnetic. Diamagnetic means all electrons are paired and paramagnetic means some of the electrons are unpaired. Next point is regarding the oxidation state. Oxygen shows -2, -1 and +2 oxidation states, while other elements show -2, +2, +4 and +6 oxidation states. So oxygen cannot exhibit higher oxidation state due to absence of vacant d orbitals. Next is the nature of hydrides. Hydrides is the anion of hydrogen H-. Hydride of oxygen, that is H2O, is liquid at room temperature, while the hydrides of other members of this group are gases. Common covalency of oxygen is 2, but in rare cases it is found to be 4. But if you look at the other members of group 16 elements, then the covalency cannot exceed 4. Covalency is the number of electron pairs that an atom can share with another atom. So overall you can say that oxygen shows anomalous behavior because it has small atomic size, it has high electronegativity and also absence of inner d orbitals. Next, we move on to study the anomalous behavior of fluorine. Now, fluorine is the first member of group 17, that is the halogen group, and it differs in properties from the other members of the group in the following ways. First is it has a very small atomic size, it has high electronegativity, again there is absence of d orbitals in the valence shell, and it has low FF bond dissociation enthalpy, which means a very small amount of energy is required to break the bond between the two F atoms. Ionization enthalpy, electronegativity, electrode potential are all higher for fluorine when you compare it with the other elements belonging to the halogen group. The ionic and the covalent radii, melting point, boiling point, and also the electron gain enthalpy are quite low when you compare it with the other elements in the group. Now, most of the reactions of fluorine are exothermic, which means heat is given out. And what is the reason for that? Because short and strong bond formed by it with other elements. Fluorine forms a short bond, but it is very strong bond. Shorter the bond, more energy is required to break the bond. Hence, fluorine forms short bonds with other elements. Since the bonds are short, it is difficult to break and more energy is required to break these bonds. Fluorine forms only one oxoacid, that is HOF, while other halogens form a number of oxoacids. Oxoacids are the acids which contain oxygen. Hydrogen fluoride is a liquid which has the boiling point of 293 Kelvin due to strong hydrogen bonding, while the other hydrogen halides, they are gases. So hydrogen fluoride is a liquid and other hydrogen halides are gases.